Hello everyone, welcome to Automotive Education with Emmanuel. Today we'll be talking about the Morse test. Now with high-speed motor vehicle engines, it is not generally possible to take indicator diagrams by the standard pencil type of engine indicator. The inertial effect of the moving parts of the instrument, friction, and possibility of control spring vibration restricts is used to steam, gas, and slow speed diesel engines, where the speed range is usually about 1,000 revolutions per minute. Now, for us to counter these difficulties, uh, either the fan barrel type or the cathode ray oscilloscope type indicator may not be successfully used for ascertaining the indicated power of high speed engines. So, where we cannot use the fan barrel type of indicator or the cathode ray oscilloscope type of indicator, we will have to now fall on an approximate estimate method of determining the indicated power of a multi-cylinder internal combustion engine by the use of the Morse test. And this is specifically for high-speed engines. Now, in this method, we usually put the engine under test coupled to a dynamometer, and then we run it at a certain speed. The brake power of the engine is then measured with all the cylinders firing. One cylinder is now cut out. This can be achieved in the case of petrol engine by short-circuiting the sparking plug of that cylinder. And in the case of compression ignition engines, or which we usually call the diesel engines, by interrupting the fuel supply to the cylinder. Now, as a result of cutting out the cylinder, the engine speed will drop. The load on the dynamometer is therefore reduced until the original speed is restored. By so doing, the friction and pumping losses are kept as nearly constant as possible. The brake power is again measured from the new brake load, but the result will obviously be lower than the first one. The difference between the two values of the brake power gives us the indicated power of the cut-out cylinder. Now, this procedure is adopted for each cylinder in turn. Then the sum of the results will give us the total indicated power of the engine. We should not forget that the total indicated power, which will be determined, is just a close approximation, since the friction and pumping losses while cylinder is being cut out is not the same when it is firing. Now, the test must also be carried out quickly in order to reduce the effect of cooling of the cut-out cylinder. Now, all that I've said now may seem like a lot of theories to you, but when you put some calculation to it, then it will make some sense. Now, let us use B to refer to the brake power of an engine with all cylinders firing, where B1, B2, B3, etc. will be equal to the brake power of engine with each cylinder cut off in turn. So B1 will be the brake power when cylinder number 1 is being cut off and all that. I1, I2, I3, etc. will be equal to the indicated power of individual cylinders. So I1 is the indicated power of cylinder number 1 being cut off. Yeah. Now F1, F2, F3, etc. is the friction power of the individual cylinders. Now when all cylinders are firing, the total brake power will be equal to the difference between the indicated power and the friction power of each individual cylinder which has been cut off, and then we sum those values up. With cylinder number 1 being cut off, we will have I1 to be equal to B minus B1. Now the total indicated power will be equal to I subscript 1 plus I subscript 2 plus I subscript 3 to I subscript n. This can also be rewritten as the difference between the total brake power when all cylinder is firing minus the brake power when the cylinder number 1 is being cut off, plus the total brake power minus the brake power when cylinder number 2 is being cut off, in that order. Or we can also write it as N multiplying B in bracket minus the sum of all the brake powers when the cylinder has been cut off. Remember, I said that the N is equal to the number of cylinders in the engine. So an example in this case is a 6-cylinder engine running at 2000 revolutions per minute. Now, when all the cylinders are firing, the brake power in kilowatts, which was recorded, was 40.65 kilowatts. Now, when cylinder number 1 is not firing, or in this case being cut off, the brake power that will be recorded will be 32.44, and then the rest of the other data being recorded for the rest of the cylinders. Now, our job is to calculate the indicated power, the friction power, and then the mechanical efficiency. So to do that, the data that was given to us was given in the table. Now to calculate the indicated power, which is the I part of it, the A part of the equation, is the number of cylinders times the total brake power minus the sum of the brake powers, is up to 6 cylinders, just like how it's been shown here earlier. So we have 6 cylinders, so 6 multiplying the total brake power, which was 40.64, sorry, 40.65 kilowatts, minus the sum of the brake power is when the cylinders has been cut off. So is the 40.6, sorry, that was for the total brake power. So when cylinder number one has been cut off, the brake power was 32.44, 32.44 kilowatts. Yeah. Plus cylinder number two, that of cylinder number three, that of cylinder number four, and cylinder number five up to cylinder number six, which is 31.7 kilowatts. I don't want to go through writing of all of the other figures. So we'll just have to, you know, calculate it. Now let's put this into our calculator and see. Calculator, good, good. So we have a 6 multiplying 40.65 kilowatts. The answer is 243.9 kilowatts kilowatts minus the sum of everything else which is there, minus the sum of everything else when the cylinders has been cut off, 192.8. So 192.8 kilowatts. Now the engine number of cylinders in the engine is 6. So when you use that to multiply the total brake power when all cylinders are firing, which is 40.65, the answer is 243.9 kilowatts. Then we will subtract the 192.8 from it. That gives us 51.1 kilowatts. 51.1 kilowatts as our indicated power. So what we'll have here will be, sorry, not 6, yeah, will be 51.1 kilowatts. This, we can do that and put it in. We did it earlier, so yeah. Then we've been asked as well to calculate the friction power. If you could recall, the friction power is equal to the indicated power minus the brake power. Basically all the components that results in reduction in the power that is being generated in the cylinder is what we are trying to find over here. So the power that is being expended at those components. So the indicated power was 51.1 kilowatts. We'll subtract the brake power from it, which is the brake power recorded. The output shaft is 40.65 kilowatts. So when we do this calculation, what will be our friction power? So 51.1 kilowatts minus sorry, minus 40.65 is 10.47. So our friction power is 10.47 kilowatts. Now we've also been asked to calculate the mechanical efficiency. Yeah, which we receive by a mechanical efficiency. Now for mechanical efficiency, now we want to see the power that is being output, which is basically the brake power, over the indicated power, multiplied by 100 to convert it into percentage. So the brake power was 40.65 40.65 kilowatts. The indicated power was 51.1 kilowatts. When you multiply that by 100, the value in percentage will be, let's calculate that. So 40.65 divided by 51.1. When we multiply that by 100, we should get, sorry, 79.57. 79.55. 79.55%. That is the mechanical efficiency of the engine. I hope that makes sense to you, all that we've done so far. Now, to recap what we've done, the Morse test is all about trying to find an approximate power that is being developed in the cylinder by trying to cut off cylinders whilst recording the power output at the output shaft. So when we cut off cylinder number 1, we record the power at the output shaft after trying to readjust the speed to the level that it was when we started the test by recording the overall brake power. So in mathematical terms, we're trying to like quantize it. We'll realize that the brake power, which will, in this case, we are denoting to be B, which is the total brake power for all cylinders that are firing, B1, B2, B3, whatsoever, and to Bn is the brake power that is for the cylinder that is being cut off. Is the brake power when that cylinder is being cut off. And then we can find the total brake power by finding the difference, the sum of the difference. So basically is the sum of the difference between the indicated power for that particular engine that is being cut off and the friction power for that particular engine that is being cut off. Yeah, is the algebraic sum of it. And yeah, and then we went on to look at the other ways that we can express the indicated power, the total indicated power, and then we look at an example. Now, that is all for today on Morse test. I hope you enjoyed it. Give me your feedback, subscribe, and hit the like button. Give me your comments down below, and then let me know what I can do to better these sessions. Thank you.